Hey everyone, welcome back. If you've been following the series, you'll remember the central argument we made in the previous video, that the real breakthroughs in modern AI haven't come from data alone. They've come from structure. We looked at how convolutional neural networks brought spatial structure to image recognition, how AlphaGo embedded the rules and strategy of the game into its learning process, and how AlphaFold encoded the physical and chemical constraints of protein geometry to crack one of biology's hardest problems. The pattern is consistent. Whenever AI makes a genuine leap, it's because someone found a way to bake the right structure into the model. Today we're going deep on one of the most compelling examples of that principle: PINs, physics-informed neural networks. These are models where the structure being embedded is nothing less than the laws of physics themselves, expressed as partial differential equations. The idea sparked an explosion of interest across the research community, and since 2019, PINs have been applied to fluid dynamics, materials science, biomedical modeling, climate prediction, basically anywhere a PDE shows up. But if you've ever actually tried to train one, you know the frustration. It won't converge. The accuracy is terrible. It's way too slow. In this video, we're going to cut through all of that. We'll cover where PINs came from, why they fail, and most importantly, how researchers around the world are solving those problems right now. Let's get into it. So where did this idea come from? The history of PINs goes back further than most people realize, all the way to the 1990s. In 1990, Li and Kang first proposed using neural networks to solve differential equations. 2 years later, in 1992, Psychogios and Ungar took it a step further by embedding physical conservation laws, mass balance and energy balance, directly into the network structure. They called it a hybrid learning method and showed it generalized better than purely data-driven models. Then in 1998, Lagares, Likas, and Fotiadis successfully solved both ODS and PDEs by designing trial solutions that automatically satisfied initial and boundary conditions with a neural network handling the rest. It was genuinely promising work. But compute resources at the time were limited, and the ideas stayed largely dormant for about 2 decades. The turning point came in 2019. Maciar Raissi, Paris Perdikaris, and George Karniadakis, then at Brown University, published Physics-Informed Neural Networks, a deep learning framework for solving forward and inverse problems involving nonlinear partial differential equations in the Journal of Computational Physics. The core idea is elegant in its simplicity. You construct a loss function with 3 components. The loss function, shown on screen, has 3 components. The first, L_PDE, measures how well the network satisfies the governing equations. The second, L_BC, captures how closely it matches the boundary and initial conditions. And the third, L_data, measures how well it fits any available observations. All 3 are computed via automatic differentiation and minimized simultaneously. The message was powerful. No mesh required, works with sparse data, and handles both forward and inverse problems in a single unified framework. That combination hit the research community like a shockwave. According to Google Scholar data, the number of PINN-related papers has roughly doubled every year since 2019. The application space has expanded dramatically. Fluid mechanics via the Navier-Stokes equations, structural mechanics, material science, cardiac electrophysiology, blood flow, seismic wave propagation, wind and geothermal energy forecasting, quantum mechanics. Essentially, anywhere a PDE appears, PINNs have shown up. The ecosystem has matured too. Open source libraries like DeepXDE, NVIDIA PhysicsNemo, formerly Modulus, SciANN, and the JAX-based JAXPy have dramatically lowered the barrier to entry for both research and industrial deployment. Now, here's the honest part. PINs are powerful, but they have well-documented failure modes. Let me walk you through the 5 most important ones. Neural networks have a fundamental tendency to learn low-frequency components of a function quickly while struggling badly with high-frequency components. This is called spectral bias or frequency bias. Rahman and colleagues in 2019 established this theoretically. Wang and colleagues in 2021 then confirmed the same bias exists in the PINN setting using neural tangent kernel analysis. For problems with multiscale behavior, turbulence, high-frequency oscillations, sharp gradients, this bias causes severe accuracy degradation. The network learns the smooth background but misses the fine structure entirely. When you use a PINN to solve a time-dependent PDE, an initial value problem, something counterintuitive can happen. The network can learn to satisfy the PDE residual at late times while leaving a large residual near time zero. Information from the initial condition simply fails to propagate forward through the domain. The result is a solution that looks converged by the loss metric, but is physically meaningless. It's essentially learned the wrong solution by violating the causal structure of the problem. For long-time predictions, this can cause complete solution collapse. The different terms in the PINN loss function can have gradient magnitudes that differ by several orders of magnitude. If the gradient of the PDE loss dwarfs the gradient of the boundary condition loss, the optimizer will focus almost entirely on satisfying the PDE, while largely ignoring the boundary conditions. The result is a solution that looks good in terms of total loss, but doesn't actually satisfy the constraints you imposed. Neural tangent kernel analysis has given us the theoretical framework to understand this. The convergence rates of the different loss components are simply not aligned. High Reynolds number flows, stiff chemical reaction networks, multi-scale material models, these all involve what's called stiffness. Vastly different characteristic timescales or length scales in the same problem. For pins, stiff problems create highly irregular loss landscapes where gradient-based optimizers get stuck in local minima. Standard atom, or LBFGS, often can't escape. Finally, in large-scale or high-dimensional problems, the placement of collocation points, where you evaluate the PDE residual, has an enormous impact on accuracy. Uniform random sampling misses regions where the residual is large, and in three-dimensional or high-dimensional settings, computational cost scales badly, making naive approaches simply infeasible. Now, here's the good news. Researchers have identified the root causes of these failures, and they've developed targeted fixes. We're going to look at three. The fix for causality violation is elegant: train in time order. Wang and colleagues in 2022 proposed a causal weighting scheme. Instead of evaluating the loss uniformly across the entire space-time domain, you weight each training point based on how well the earlier time steps have already been resolved. Points at large, t only receive gradient signal once small t is under control. This forces information to propagate forward from the initial condition, exactly the way physics demands. The fix for loss imbalance comes directly from theory. Neural tangent kernel analysis reveals the exact mechanism. Each loss component has a different set of eigenvalues, which means different natural learning speeds. Wang and colleagues in 2021 used this insight to derive adaptive weights that rescale each term dynamically during training. The result, the boundary condition loss and the PDE loss converge at the same rate. The optimizer stops ignoring the constraints you impose. The fix for the sampling problem is to make sampling dynamic. Liu and colleagues in 2021 proposed residual adaptive refinement, RAR. The idea is simple. Periodically evaluate the residual across the domain, identify the regions where the error is still large, and add more collocation points there. Instead of spreading points uniformly and hoping for the best, you concentrate computational resources exactly where the network is struggling. We've covered a lot of ground. Physics-informed neural networks are a genuinely powerful idea. The ability to embed physical laws directly into the learning process without labeled data opens doors that traditional numerical methods can't reach. But they're not magic. Spectral bias, causality violation, loss imbalance, stiff landscapes, poor sampling. These are real failure modes, and they can silently produce solutions that look converged but are physically wrong. Here's what I want you to take away. The researchers who identified these problems didn't give up on pins. They went deeper into the theory, into the mathematics of how neural networks actually learn, and they found targeted fixes: causal weighting, NTK-based balancing, residual adaptive sampling. Each one addresses a specific structural weakness. That's the pattern this entire series is built around. AI breakthroughs don't come from scale alone. They come from encoding the right structure, understanding what your model is actually doing, and shaping the learning process to respect the problem's geometry. Pins, when done right, are a beautiful example of that principle in action. Is there a topic you'd like me to cover? A paper, a model, an idea you've been curious about? Leave it in the comments. If this was useful, subscribe and leave a like. It helps more people find this kind of content.